So let's get down to the nitty-gritty and see what information we can glean from our guest today. And I'd like to start with Dr. Seth Lloyd from MIT. Now, most of us see information as something that you just read or you copy or you share with somebody else. What's that got to do with physics?
Well, everything. Sorry, did you want a longer answer than that?
A little longer. This isn't the news. Sorry.
So Bob, actually, 150 years ago, people weren't so concerned about information because they weren't living through an information processing revolution. But 150 years ago, a bunch of physicists, James Clerk Maxwell at Cambridge and Edinburgh, Ludwig Boltzmann in Vienna, Josiah Willard Gibbs at Yale, they actually discovered the fundamental formula that described information. And they didn't describe it in terms of bits. They discovered that formula because they were looking at how atoms move around. And they wanted to quantify this funky stuff called entropy. Now, entropy was at that time known as a quantity that gummed up the works of heat engines, of steam engines, and kept them from doing the amount of work you'd want them to do. But phrased in modern terms, what Maxwell, Boltzmann, and Gibbs discovered was that entropy is actually information. It's bits. So these atoms, as they move around, they carry bits of information with them. And every time two atoms collide, those bits flip. So in fact, not only does information have everything to do with physics, but physicists actually discovered it to begin with.
And it could also be what, now we have light that's carrying information, like fiber optics. So it could be a quantity of light as well.
Yeah, so if you want to see, if you were looking at how the information processing revolution came about, it's because scientists and engineers figured, oh, everything's already got this information associated with it. Let's use it. You know, a particle of light, a photon, it can have a bit of information, like if it's wiggling back and forth like this. So if I take, my Ray-Bans, I put it like this, photon wiggling back and forth like that, you can call that a 0. Photon wiggling back and forth like this, Ray-Bans like that, you can call it a 1. So all these, particles, physical entities have information associated with them. And when we build things like quantum computers, all we're doing is just taking advantage of that.
So does that mean then that information is limited by the laws of physics?
Darn tootin'.
Another precise answer there.
Wow.
Let me turn to Chris Fuchs.
Sure.
From Perimeter Institute. Can you give me an example of how the laws of physics allow us to do things with information?
Oh, well, I certainly can. But I think, actually, just to follow up on Seth first.
Okay.
I've got to tell you about the first time I saw Seth Lloyd in public. He was emphasizing at that time not that everything can carry information, but that everything could be used to compute. And to make this dramatic, I remember him pulling off his shoe and putting it on the overhead projector and saying, you could even use this old shoe to compute. So when he says these things, he's serious about it. So what was your question?
Now, Dr. Susskind, how do you define information?
Well, I think I would call information everything that you need to know about a system to know what happens next. So, for example, if you had a bathtub full of hot water, what information do you need to know in order to know whether to get into that bathtub or not? Well, you need to know its temperature, you may need to know its volume, to know if there's enough water there and so forth. But that's a very limited amount of information. There's an enormous amount of information stored in the position and velocity of every single molecule in the water. If you really want to know exactly what's going to happen next, you need to know the position and velocity of every single molecule in that water. So there's an enormous amount of hidden information that you don't ordinarily see when you look at the bathtub full of water. That hidden information, the information that you can't see, is what's called entropy. And if you really want to know in detail what will happen next from any given initial starting point, you need to know all of the information, which means everything that can be known, all the numbers, all the velocities, all the positions, which are the maximum amount that you can ever know about that bathtub full of water. And if you knew it, you could predict what will happen next. That's what I call information.
Now, how close are we? I mean, that sounds to me like a huge amount of information. How close are we to actually knowing that? Just in a bathtub full of water.
Well, usually when I get into the bathtub, I know the temperature and the volume, and that's about it.
So the physics doesn't seem to be playing a lot.
Right. Right. There's an enormous amount of hidden information that you can't see, and it goes under the name of entropy.
But I want a definition here, the difference between what we think of as classic physics and quantum physics.
Yes.
Okay, so-
Yes. I think in principle it really is the same thing, but I'm afraid that to give you the sharp distinctions between classical and quantum, I would have to give you a course in quantum mechanics.
We don't have time for
So, no, we don't have time for that. So I would suggest that you come to my evening course at Stanford, which we call Quantum Mechanics for Old People. And about as many people here come once a week to find out what quantum mechanics is. It's also on the internet.
Okay.
Yeah, the character of quantum information is a little bit different than the character of classical information. It's a little more coarse-grained. In some sense, it's not quite as detailed. The uncertainty principle prevents you from knowing all the things that one would think one could know classically. So it takes a little bit less information in a certain sense to know what the quantum state is doing. On the other hand, it again corresponds to knowing the enormous amount of microscopic information that's in that bathtub full of water.
Okay. Let's bring Tony Leggett from University of Illinois into this discussion. How do you define information?
I think fairly similarly to what Dr. Siskind has done. As far as I'm concerned, information always has to be about something, and it has to be embodied in something. And so I think a typical example of useful information is a map. A map represents certain properties of, let us say, a city. Generally speaking, it does not represent all the properties, but it represents those properties that you want to know about at any particular time, and it represents it according to a particular scheme. In this case, it represents it on a two-dimensional sheet of paper. And I think there's a famous statement by Rolf Landauer which says that information is physical, and I take that to mean that it has to be, you don't get your information free, it's always got to be embodied in something.
I think a better thing that Landauer could have said is information carriers are physical. I think
Yes.
that would capture your
Well,
point.
it would, yes.
Dr. Susskind?
Yeah, let me completely disagree with you. No.
I was almost
Not at all.
getting it.
Let's just clarify a point. For example, the information that Waterloo is north, is it, of Kitchener? Or is it south? I don't
Yes,
remember.
north.
But that information is not contained on the map. That information is contained in Waterloo and Kitchener. Your map and my map might actually be different, and we don't know that until we look at the maps. And all the information on the map is that my map says that Waterloo is north of Kitchener, and your map may say something different. The actual information about the fact that Waterloo is north of Kitchener is contained out there on the surface of the Earth, where Waterloo and Kitchener are.
Is there any information that's not physical?
No.
None.
Yes.
No. Oh, yes.
Oh, yeah?
You know, there's a lovely phrase I like by one of the inventors of Bayesian probability theory, who says probabilities do not exist. And by that he meant to capture the idea that there's a distinction between the world as it is. There's Kitchener and there's Waterloo. And you don't even have to say the word information to put one north and one south. You can just say there's Kitchener and there's Waterloo. And then there's what someone knows about it. Oh, God, I can't remember whether Kitchener is south of Waterloo or east of Waterloo. And you look on a map, or you actually look at the things and you get surprised. And then because you're getting surprised, you're getting information. So just like the probabilist said, probability does not exist, that means it's not out in the world. I would say information's not out in the world, it's in your head.
Ooh,
The
okay.
stuff out in the world's out in the world.
Let's move into what we can do with information. And Dr. Lloyd, I understand you were actually a consultant for the movie The Matrix.
No, for the movie The Physics of the Matrix. It was
No.
about...
You're right, the physics of the Matrix.
There you go.
Okay. And you were also on my show on Quirks and Quarks talking about your book, Programming the Universe. So,
Kind of you to mention it.
so is the universe really like the Matrix, a giant computer program that we're actually living in?
Do you want the short answer or the long answer?
Medium would do well here.
Okay. All right. So I'll have to average them. Well, the short answer, of course, is yes. I mean, it was established 150 years ago that everything contains information, and that every atom has bits around. Every time they collide, these bits are flipping. This table, this glass of water, this shoe, yeah. They're just full of information, and they're processing it right and left. I guess it's a boot. So, yeah. So the short answer is yes. But then if you actually want to, but that's something that's really not very controversial. The time to object to that was around 1900, and people failed to, so that's pretty well established.
But what do you mean when the universe is a computer?
Yeah, so there's more, you can say, okay, it's processing information at its most microscopic levels, therefore it is a computer. That's good enough for me. But you might also want to know, okay, the universe is a computer, why isn't it running Windows? Well, maybe it is.
Windows 14 billion.
Well, I would prefer if it ran Linux, actually. That would be. I'm more an open source person for this. But in fact, now we actually know the universe can do stuff like that, because my colleagues and I, for now more than 12 years, have been building quantum computers where we actually build computers that store bits of information on individual atoms. One atom, one bit, to paraphrase the U.S. Supreme Court, at least for the moment. So, yeah, so we can actually build them, and indeed, everything out there that we look at, when we look at it close enough, it's computing.
Well, give me an example of a universal computation.
What the universe is.
What's the universe computing? Like, give me an example.
Oh, well, it's computing itself. It's computing you, for one thing.
Is the answer 42?
You gave it away.
Of course we know the answer. I want to know the
Now I
calculation.
can leave. Yes.
But what do you mean by that?
Well, so you could think, if you want to think of the universe as a computer, and as I say, it's a scientific fact, it's not really a metaphor, then the universe is computing everything that we see. This table is being computed by the microscopic motions of these atoms. Lenny's bath, that got him warm and clean for this evening. That was the result of that computation. So everything that we see is a result of this computation.
So you're saying just because things are happening, atoms are spinning and molecules are jiggling and planets are orbiting stars, that's a computation?
Bits are flipping.
Bits are flipping.
They can all be described in terms of how bits flip.
What's the rest of the panel think of that?
What would be an example of a process which is not a computation?
Yeah, good question.
Maybe let me take a shot at this too. Maybe 150 years ago, people might have said the universe is a clockwork mechanism. What is the idea that the universe is a computation have that old idea doesn't have?
Well, yeah, it has the idea of information built into it. I mean, of course, you could easily accuse me, as I think you vaguely are, of saying, oh, well, we're in the midst of this information processing revolution. I own computers. I actually build quantum computers. Therefore, I think the world is a quantum computer, right? That's a perfectly reasonable accusation. That's why I was at pains to point out that this discovery that the universe is at bottom processing information was actually made by a bunch of people like Maxwell, Boltzmann, and Gibbs, who had no notion of computation at all. Yet they inadvertently almost discovered the fundamental laws of information theory.
But could you pose the whole idea without saying the word information? Could you say the universe is evolving according to some dynamical laws? It's doing it deterministically. It's doing it reversibly.
Well, yeah, absolutely.
Could you do that without saying the word information?
Yeah, you could do that.
Then what does information add?
Well, so you could also say your computer is just evolving by a set of dynamical laws, or for that matter, your brain is just evolving by some set of dynamical laws, and no information is being processed. But I'm not going to say that, because that would be insulting.
Well, sure, the universe is a computer. Anytime a system evolves according to a set of mathematical laws and goes from one state to the next according to any kind of mathematical laws, you can say it's doing a computation. What is the software? The software is the laws of physics. What is the hardware? The hardware is matter, the things that things are made out of. But ordinary computers, you can change the software. You can change the software, you can stop the computation, change the software, and have it do something else. As far as I know, there is no evidence that it's possible to change the software of the universe.
Or there could be other universes running different programs.
And there could be other universes running different programs. But I don't think anybody's going to stick their finger into our universe and suddenly change the software. Or at least there's no evidence that that will ever happen. So in that sense, it is different than a computer.
You mean you're saying that our universe is unlikely to crash at any moment?
Oh, no. It's very likely to crash. I think, I think my president has almost guaranteed that.